Okay, so last time we looked at power series. So you have a sequence AN is a sequence, and then for each x you form the new series. You form the series. And the series is where an times x to the power n, and then you're summing, you decide somewhere to start, and then you're summing to infinity like that. So something like this, that's a power series. And we looked at a particular case where the ANs, so example here is where AN is equal to 1 over n factorial. And so we got the function e of x, which is a sum from n equal to 0 to infinity of x to the power n divided by n factorial. And then we used this to, we observed that e is bigger or equal to 0 for x bigger or equal to 0. And we also observed that e of 0 is equal to 1. And we defined little e to be this function e of 1. And then we defined another function e to the q, where q here is now a rational number, right? And it was defined, in particular, e of 0 was defined to be equal to 1. E of 1 was just defined to be e, right? And then we assumed, which we will prove today, that e of x plus capital E of x plus y is equal to e of x times e of y. So we assume that. And then we saw, and then we defined, right, so this little e, this function based on the little e, in particular e to some power m, if m is an integer, is just e times itself, m times. And then we defined e to a power 1 over n here to be the positive number, as it was defined, to be the positive number. So that alpha, let's say, so that alpha raised to the power n is equal to e. Right? And we also defined e to a negative integer, and this was just to be defined to 1 over, so we defined e to minus m to 1 over e to the m. So this way we defined this function here, the power series was defined for all x, and we defined another function, little e of q, on all rational numbers q. Right? And then we assumed this here. We saw that these two functions, so e of x is equal to e. This function here is only defined on rational numbers, so they're equal when at rational numbers. So we saw that. And then in the p sets 5, I think it's for both of them, you will show, or maybe it's 1 for 4 and 1 for 5, you show that E is continuous. And you will also show that E is the, so you will also show the following. That if F and G are two continuous functions, so they are defined, both of them, both F and G are defined on the real numbers. And you assume that if you restrict them to the rational numbers, then the two functions are equal. So if they're both continuous and they agree on the rational numbers, then actually they must agree everywhere. On all of R. Okay, so in other words, this one here, you know, this is a function by P sub 5. It's a function that's continuous on all of R. It's agree with this function. And so this is the only extension of this function to be continuous and defined on all of R. Okay, so now, but we still needed to prove this relationship here that we assumed. So let's try to prove this one here. And I'll just do the main case of it. And so we're going to prove, so theorem, we prove that E of x times y is equal to E of x times e to the y. And I'm going to show this proof in the case where these are non-negative numbers, both of them. The general case is once you have this, is the general case. It's not very difficult, but I won't do the general case. Now, how are we going to prove that? So to prove that, we're going to use another theorem. So the other theorem is that, so we take two, suppose you take two series of each of them are of non-negative numbers. So, so the setup is, so again, this is going to go into the proof of that theorem over there. But the setup for this theorem is more general. I take a series AN, and I take another series BN. And I'm assuming that both AN and BN for all n are non-negative. So for all n. So these are a series of non-negative numbers. And then I form another series. I will form a third series. And that third series is going to be defined from the two previous series. And, and the third series, let's call it Cn, like this. And now Cn here is going to be the sum of AI, B, n minus I equal to 0 to n. So this has the effect of that the index of this plus the index of that is always adding up to n, right? So the sum of the two indices is exactly n, right? Okay, so that's, so obviously, so note note that the CNs here are, of course, also non-negative. They're just sums of non-negative numbers. Right? So this is a new series, right, of non-negative numbers. And then the theorem is, that if these series here, this one here, and this one here are convergent, then this series here is also convergent. And we also have that the sum here, that this sum here, that this sum is just a product of the two sums. So it's a product of the sum here like that. So again, we have these two series of non-negative numbers. From those two series, you form a third series. And the third series, the idea is that the third series is kind of like a product of the other two. And it's the CNs in the third series is given where you take the sum of the products of the elements in the other two so that the index is at n. And then if the two series you started with are convergent, then this product series is also convergent. And the sum of the product series is really the product of the sum of the other two series. Okay. Now, so that's what we want to prove. And then once we have this, we're going to use it to prove this theorem here. And so now to prove it, let me just first observe that. So let me observe over here that right. So let me make a couple of definitions and then making an observation. Let me start with making some definitions that is useful in the proof. So I'm going to define S and A just kind of like we usually do, where we're summing here from I equal to 0 up to n of AI, right? The superscript is come from the series, the A series. And then likewise I define S and B to be the sum here of the BIs. And then I'm defining S and C to be the sum of the CIs. Oops, up to n, like that, right? And so, of course, you have that we know that AI, BI, and CI are all non-negative numbers. So this means that convergence of any of these series right, so convergence, say, of this one is the same as saying that these numbers here are bounded. Right? That's by monotone convergence. So convergence of any of these series is equivalent to that the corresponding Sn, A, B, or C, A, B, C are bounded. Okay, so that's just an observation. And again, this is the monotone convergence theorem. This is by monotone convergence theorem. Okay. So that's a monotone convergence theorem. The other thing, let's see, I thought of something else I wanted to note. Right. Okay. So let's try to prove that. So to prove it, let me just try to think about it for a second here. So if I'm looking at A1, say A2 plus up to AN. Suppose I'm looking at this here. This is like Sn A, right? And I have that SNA, and suppose I'm now looking at the SNB. This here is the SNB. Now, if you just multiply out the product of these two, right, then you would get, and I should have started at 0, sorry. Let's start at 0 because that's what we do up there, like that. Okay. So now I multiply out, and you see that you're getting A0, B0, and you're getting, then you can kind of, if you try to do it, so let's try to multiply this out, but let's do it in an ordered way, okay? And when I'm talking about ordering way, I'm not talking about just multiplying this one on that. I mean, you could say that's very ordered, but it's not related to what the C series. So I want to just group things so that they remind us of the C series. But if I do that, so when I'm starting with this is this multiplied by this, then I take this one here multiplied by that. So A0, B1, right? This here is the only one where the index, the subscripts are non-negative integers. This is the only one where the sum of the two subscripts is 0. Right? If I'm looking at where the sum of the two subscripts is 1, this is one of them. But there's another one, and that's where I take this multiplied by that. So I sort of group those together. So A1, B0. And now I want to collect the ones. So those are the only two where the sum of the subscript is 1. Then if I'm looking at when I'm multiplying out, where the sum of the subscript is 2, well, I could start with this one, but then I have to pick B2. So I take plus A0, B2. Then I could take A1, B1, right? That has also sum of subscripts 2. And the last one is if I take A2, but then the B have to be the 0 subscript, right? And now I proceed like this, so I'm grouping it like this. Okay, now of course, there's going to be a little bit of an issue. So for a while, everything is, you see that this thing here, this here is what we call C0, this here is C1, and this here is C2, right? And then we presumably also get C3. But then there is a point where we sort of run into trouble if we want to really do it like this. So, so what we get is that, so when you do this multiplication, what you will see is, so you see like this, A0 plus A1, AN. What you will see times B0, B1, to be in. But you see that this pattern here, it's continue for a while, and you're getting that this is equal to C0, C1 plus C2 up to Cn. Cn, in the Cn, right, this is again where the sum of these indices could be this one here multiplied by that. The sum of the subscript will be n, right? But if you're now looking at the next one, that what it corresponds to Cn plus 1, you're not getting all of the Cn plus 1, because like one of the Cn plus 1 would be like a to the n plus 1 times p0, but you don't have that one here, right? So what you get is that you're getting all of these plus something additional. Okay? And the additional is because everything is non-negative, the additional thing is a non-negative number, right? Okay, so what we have established here is that we have, so this here show that SNC, this is here, this here is, let me just write it like this. This here is SNC. So you see that, and this here was SN. This here was S. This here was, right, this thing here was SNA, and this here was SNB, right? So what you have is, so this inequality just tells you that SNA times SNB is equal to SNC plus something positive, non-negative. So in other words, this number here is less or equal to the product of these two. So this implies that SNC is less or equal to this here. But now you see you already have something. Because these here was increasing, right? They were increasing because the AN was all non-negative. So these here are increasing, and they are less or equal to, right? The series was supposed to be convergent, so you have that, sorry. So here I'm using that the SNA is monotone increasing up to the limit here. Right, and likewise the SNBs here were monotone increasing up to the limit. Right? So this thing here, so this is smaller than the limit. This is smaller than the limit of that. So this thing here is less or equal to the product of these guys. Right? And so you see, and that's supposed to be just a real number, this here. So you see that these guys here are now bounded. So this means that because they're monotone, it means that that series is also convergent. So what we have concluded here is, what we have concluded here is that this series here is convergent, and we have that this infinite sum here is less or equal to the product of the other ones. Right, this is what this here gave us. Right, so this is what we have so far. Okay, now we want to get the reverse inequality also. Right, so we want the reverse inequality of what is over there, so that we can say that those two things here are actually equal. Right. Now let's try to see how do we prove this, the reverse of this inequality. The reverse we're proving it by examine more closely what that product was. So you see, so what is this additional thing here? So again, so we're looking at this thing here. And what we got is that this here was equal to the sum here of Cn, but then we have some additional terms, right? And the additional terms is, the thing is that if you start looking at the additional terms, so what are the additional terms? You're getting a A1 Bn, right? That's one where the sum here is n plus 1, right? And then you also get, so this is coming from this, that one here multiplied by this. You would also get a A2 Bn minus 2. You get a A3 B, sorry, not n minus 2, n minus 1, B3 n minus 2, right, etc., right? So, but all of these here, and then, right, so you get that. But you don't get, again, you don't get the one that is missing here. Is A0 Bn plus 1. This one is missing, right? And the other one that is missing is this one here. But otherwise, you get all of the ones that was in the Cn plus 1, and you don't get anything more, right? And so this pattern continues. So like the next term would be like A2, sorry, yeah, and then you would also get something where the sum of the indices was 2. That's like A2 Bn, right? But here you'll be missing more, right? You'll be missing A0 Bn plus 2. You're missing A1 Bn plus 1, right? But you don't get anything more, right? And so the thing is, like when you continue like this, the last one you get is like when you're multiplying that by that. And that's An times Bn. Those here, the sum of the indices is 2. 2n, sorry, right? It's 2n. But you're missing a lot now, right? I mean, you only have one of many, many terms, right? But but it is a term that all appear, and this one would appear in C2n. So in this way, what you have is that this here is less than S to the power 2nc. Right? They are all in there, but you will be missing terms, but all terms are non-negative. Right? So this means that you have that inequality. Right? So you see that now what we have here is that we have what we established before was the inequality that SNC was less than SNA times SNB. But what we have now here is that this thing here, this product, is less than S2NC. Right? This one here is squeezed between this one here and that one here. But both these here converge to the same. Right? They both converge to this infinite sum. Right? So these here converge to the same. This means that this here, the limit of this here, must also be the same. Right? And so this shows that this here is the reverse inequality. So proof over there, right? Okay, so now, so that's, okay, so this is that if you take two series and you form the product, then that also converges if the two series is non-negative numbers. So let me just make a corollary of this. that, of course, if you take a series here, and so I'll just do a trivial corollary, but you can see how you can use this. And this is kind of used in proving the general case. So we will only, okay, so suppose I take two series here. So this is a trivial corollary of it. Suppose I take two series here, and I know that this one here, that they're both absolutely convergent. If they're both absolutely convergent, then if you take this series here, Ci, well, this one here I claim is also absolutely convergent. And again, this sort of trivial corollary is the key ingredients in proving a more general statement that would be used, say, to prove this inequality here when x and y are non-negative, are not assumed to be non-negative. But I won't get into that. But I'll just make this observation and get this corollary. So I claim that this thing here is also absolute convergence, right? So again, I'm not assuming now a sign on these, but I am assuming that they're absolutely convergent. Right? And so if they're absolutely convergent, so prove. So absolutely convergent. This just means that the series here, this one here, and this one here are convergent. Right? That's what absolute convergence means. But now if you're looking at Ci, the Ci series, this here is the sum here, I equal to 0 to n of ai b n minus I. Okay? But this means that Ci absolute value here is less than this thing here, absolute value, like that. You can take the absolute value sign in under the summation sign. So this is less than the sum here from I equal to 0 to n, and then ai times b n minus I, like that. Right? But now you see that this here is the corresponding C. So you could now define. So you start with the sequence AI, and I now defined a new sequence BI bar, and I do it by just taking the absolute value like that. So I know that this new series is convergent. Likewise, I defined BI bar to be the BI absolute value. And I know that this is convergent. And then I defined a sequence here, CI bar, which is just the absolute value of the CIs. And I know that this one here, so I know that this here is convergent, that's by assumption. This one here is convergent by assumption. And this inequality here proves that this here, that the CI bar is also converging, because this one here is the one where you form the products of these two convergent sequences. So this one here is also converging. So this here is also converging. By the theorem. Okay, anyway, there was just an observation that we're getting this sort of statement out of it. Okay, now this is also related. So why do we have non-negative here, right? Or why do we talk about absolute convergence? So this is a simple fact that if you take a series, if you're trying to sum infinite numbers, right? We now know how to sum infinite numbers. But if you're trying to do it, if the numbers that you're summing are all non-negative, then actually the ordering doesn't matter. You can check, you can take the fifth element first, and then the seventh, and then the 119, and then come back and take one. It doesn't matter what order you do it in. But if the numbers are not non-negative, then and the series is not absolutely convergent, now it suddenly matters. Because you could end up taking all the negative numbers first, and then you get really, really far down to, to minus towards minus infinity. Then you take a few of the positive elements, and then you take more of the negative, and so then you would actually stay very far down towards minus infinity. And you would never be able to come up again. I mean, so this is like a basic fact that if you take a series and the series are of non-negative numbers, then actually and it's converging, then you can rearrange the ordering and it will still converge, and it will still converge to the same number. If you're trying to sum infinite numbers and they are not non-negative and they don't converge absolutely, then the ordering does matter. Okay, and this is related to why we are assuming that all of these AI, BIs are non-negative numbers. And okay, but we won't get into this. I mean, you can read about it. It's a sort of standard fact. It's certainly somewhere in the book, but it's not part. Yeah.